Hi everyone, this is your Kinematics in 2 Dimensions practice quiz. It will cover projectile motion, uniform circular motion, and non-uniform circular motion. And these are the 5 questions I want you to answer. So pause this video and try them for yourself. And now for those of you who like seeing the answers right away, here they are. Now let's dive in to how I solved each of these questions, starting with question 1. In this question, a car is driving with a velocity of 10 meters per second. It then drives straight off of a cliff. Now, if the car lands 50 meters away, how tall was the cliff? First things first, I hope you recognize that this is projectile motion because the car will have a parabolic trajectory, and the only force acting on it as it falls will be the force of gravity. Now, the first thing we want to do is look at what was given. And remember, when we're dealing with projectile motion, we have an x component and a y component. The x component is uniform motion, which means we can use our uniform motion equation that says Vx is equal to delta x divided by delta t. We know delta x is equal to 50 meters and Vx is equal to 10 meters per second. Now let's look at the y component. The y component of projectile motion is free fall, which means we can use our kinematic equations. Now let's look at what we know for the y component. We know the initial velocity in the y component is 0 meters per second. I know that because all of the velocity is in the x component. I also know the acceleration in the y component will be equal to negative 9.8 meters per second squared. That's the acceleration due to gravity. And we know the final position of the car will be 0 meters, because it will land at the bottom of the cliff. And now just to make it clear, we are solving for the initial position, yi, because that represents the height of the cliff. Now that we know what we were given, let's go over our plan for solving this question. What we are going to do is we're going to use the x component to solve for delta t. Then we're going to plug delta t into the y component, and we're going to use this kinematic equation to solve for yi, the initial position of the car. Starting with the x component, we can use the uniform motion equation, which says Vx is equal to delta x divided by delta t. And then we will rearrange this equation so we can solve for delta t. Now all we need to do is plug in our values, and we find that delta t is equal to 5 seconds. Now that we have delta t, we have everything we need to solve for yi using this kinematic equation. So I will plug in my values and rearrange for yi. And what we find is that the height of the cliff is 122.5 meters. And that's the answer to this question. Now let's move on to our second question. In this question, we have a ball, which is being thrown from a height of 1 meter with a velocity of 5 meters per second. And we want to know how far does the ball go if it is thrown with a 30-degree angle. And now again, this is a projectile motion question, and the first thing I like to do is write what was given. We know we will have an x component and a y component. Let's start with the x component, which is uniform motion, so we can use our Vx is equal to delta x divided by delta t equation. And now in this case, we can solve for Vx, because remember, Vx is equal to v cos theta. Now if you don't know where I got that from, remember, if the velocity vector is at an angle, we can break it up into an x and y component. So we have Vx and Vy. Then we can use vector addition to add Vx and Vy tip to tail, with the resultant being v. And now we have a right-angled triangle. And we can use our trigonometry to solve for Vx and Vy. Starting with sine, we know sine theta is equal to opposite over hypotenuse. The opposite side is Vy, and the hypotenuse is v. Rearranging this, we get Vy is equal to v sine theta. Now on to cos, we know cos theta is equal to adjacent divided by the hypotenuse. The adjacent side is Vx, and the hypotenuse is v. When we rearrange this, we see that Vx is equal to v cos theta. And that's how you find the x and y components of the velocity vector. And so looking back at our Vx equation, all I need to do is plug in the values for V and the angle, and we find that Vx is equal to 4.3 meters per second. Now let's look at the y component. Remember, the y component is free fall, which means the acceleration in the y component is the acceleration due to gravity. So that's negative 9.8 meters per second squared. We also know the initial position of the ball, which is 1 meter, the final position of the ball, which is 0 meters because it lands on the ground, and we can solve for Vy using V sine theta. All I have to do is plug in my values, and we find that Vy is equal to 2.5 meters per second. Now that we know what was given, let's work on our plan. Now we know we are solving for delta x, which means we want to use our Vx is equal to delta x divided by delta t equation and rearrange for delta x. Looking at this equation, we are missing delta t, so we will use the y component to solve for delta t. Specifically, we will use this kinematic equation. And I chose this kinematic equation because we were not given any information about the ball's final velocity. And this is the only kinematic equation that does not include Vf. So now, using this kinematic equation, we will plug in our values and simplify. And what we're left with is a quadratic equation in the form ax squared plus bx plus c is equal to 0. And in this case, a is equal to negative 4.9 meters per second squared, b is equal to 2.5 meters per second, and c is equal to 1 meter. Now how do we solve for delta t when we have a quadratic equation? Well, you need to use the quadratic formula, which says that delta t is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a. And now looking at this quadratic formula, we have a plus and a minus, which means there's two possible solutions. We have negative b plus the square root of b squared minus 4ac divided by 2a, and we have negative b minus the square root of b squared minus 4ac divided by 2a. And now one of these solutions will be correct, while the other will not be possible. Let's start with the first one. When I plug in my values, I find that delta t is equal to negative 0.26 seconds. Time cannot be negative, so that answer is incorrect. Now let's try the other equation. When I plug in my values, I find that delta t is equal to positive 0.77 seconds. So that is our correct answer. But remember, we're solving for delta x. So what we need to do is take our uniform motion equation, rearrange it for delta x, and then plug in our values for Vx and delta t. And what we find is that delta x is equal to 3.3 meters. And that's the answer to our second question. Let's move on to our third. Now this is our last projectile motion question in this quiz. In this question, we want to know what is the maximum height a car reaches if it launches off a 5-meter tall ramp with a velocity of 10 meters per second at a 45-degree angle. And now the key to this question is remembering that at the maximum height, Vy, so the y component of the velocity, is equal to 0 meters per second. If you remember that, this question is easy. Let's dive into what was given. And now normally with projectile motions, I talk about the x component and the y component. But in this case, we only need the y component, which I hope you remember is free fall motion, which means the acceleration in the y component is negative 9.8 meters per second squared. We also know the initial position of the car is 5 meters, and the final position of the car is actually what we're solving for, because that represents the maximum height. And we know that at the maximum height, the velocity is equal to 0. And we can also calculate the initial velocity in the y component using v sine theta. All I have to do is plug in my values, and we find that the initial velocity in the y component is about 7.1 meters per second. And now based on what was given, we can use the Vf squared is equal to Vi squared plus 2a delta y kinematic equation to solve for Yf. All we have to do is rearrange this equation to isolate for Yf, Once that's done, we can plug in our values, and we find that the final position is 7.6 meters. And that's the answer to our third question. Let's move on to the fourth. In this question, we have a Ferris wheel with a diameter of 20 meters, and we are told it's spinning at a rate of 2 RPMs. And we want to know what centripetal acceleration a rider on this Ferris wheel would experience. Now remember, centripetal acceleration can be calculated using this equation, which says the centripetal acceleration is equal to v squared divided by r. V is the speed of the object going in the circle, and r is the radius of the circle. Now remember, v is equal to 2 pi r divided by t. T is the period of the motion, and that's what we need to calculate. Now we were told that the Ferris wheel is spinning at 2 RPMs. So how do we convert RPM to period? Well, all you need to do is take 1 divided by the number of RPMs. When we do that, we get 0.5 minutes per revolution. And now the period should always be in seconds, so I just need to do a unit conversion. And what we find is that the period is 30 seconds. Now that we have the period, we can solve for the speed, using v is equal to 2 pi r divided by t. All I have to do is plug in my values for the radius and the period, and we find that the speed is about 2.1 meters per second. And now we're ready to solve for the centripetal acceleration. All we have to do is plug in the value for the speed and the radius. And what we find is that the centripetal acceleration is equal to 0.44 meters per second squared. And that's the answer to our fourth question. Time to move on to our fifth and final question. And now this question is a non-uniform circular motion question. Here we have a fan which is spinning with a period of 0.5 seconds, but then it's turned off and slows down until it stops in 15 seconds. And we want to know how many revolutions did the fan do as it came to a stop. And now remember, when you're finding the number of revolutions, you can use this equation, which says that the number of revolutions is equal to the change in angular position divided by 2 pi. Now, how do you find the change in angular position? Well, you can use any of these three equations. And now remember, these are just like our kinematic equations, but they're dealing with angular position and angular velocity and angular acceleration. And now I will choose this equation to solve for the change in angular position. Now, in order to use this equation, we need to solve for a few variables. The first is the final angular velocity, which would be equal to 0 radians per second, because the fan comes to a stop. Then we need the initial angular velocity, which is equal to 2 pi divided by t. T is the period, and it's 0.5 seconds. When we do the math, we find that the initial angular velocity is about 12.6 radians per second. And finally, we need to solve for the angular acceleration, which is equal to the change in angular velocity divided by delta t. When I plug in my values, we find that the angular acceleration is equal to negative 0.84 radians per second squared. And now we have everything we need to solve for the change in angular position. All we need to do is rearrange this equation to isolate for the change in angular position, and then we just need to plug in our values and solve. And what we find is that the change in angular position is equal to 94.5 radians. And now we can use our number of revolutions equation to solve. So all we have to do is plug in our change in angular position, and we find that the fan did about 15 revolutions before it came to a stop. And that's the answer to our final question in this quiz. I hope you were able to answer all of these questions on your own. If you did struggle, check out my other videos on projectile motion, uniform circular motion, and non-uniform circular motion to keep practicing.